the strength of acids and bases. We have all heard somewhere people saying strong acids, strong bases, weak acids, weak bases. But what are they? What acids are strong acids? What bases are strong bases? Well, we're going to learn that today. We're going to use this generic acid ionization equilibrium to talk about what are strong acids and what are weak acids. So this is a generic acid dissolves in water. It will donate a proton to water. Water becomes hydronium ion. Generic acid becomes its conjugate base. This is for most of acids, this is an equilibrium. It goes both ways. Well, strong acid. A strong acid is an acid that can transfer 100% or close to 100% of its protons to water. If that is the case, if this HA is a strong acid now, by definition, it gives up all of its protons to water, which means this equilibrium favors far to the right, which means this is basically is not an equilibrium. It is a one-way reaction. Number one. Number two, it also means that if you dissolve a strong acid in water, the molecule of the acid will totally ionize into ions. There is no molecules exist in a strong acid solution. All the molecules will be ionized into ion. That's why it says that it donates close to 100% of its proton. So let's see. Ionization equilibrium lies far to the right. Okay, we did that. We covered that. Yields a weak conjugate base. Oh, what is that? We're going to talk about that later. Let's see what else do we have. The stronger the acid, the weaker its conjugate base. Well, what else? Okay, there is hardly any molecules exist in the water solution of a strong acid. We covered this. We covered this. These two we did not talk about. So what do they mean? Well, let's look at this acid ionization equilibrium. We do know that an acid, after donating a proton, will become a base, which is conjugate base. Now let's look at the strength of this base. What does a base do? A base's job is to accept a proton, to grab a proton from an acid. Well, in this mixture, there are tons of proton donors. Hydronium ions are great proton donors. However, according to the definition of the strong acid, this equilibrium lies far to the right, which means they do not go back. These two do not react to go backwards, which means this base, A minus, the base generated from the strong acid, the conjugate base of that strong acid, this base doesn't care about protons. With all the protons from hydronium ions around it, it doesn't take them, which means this base is weak. Does that make sense to you? So a strong acid always yields a weak conjugate base. As a matter of fact, the stronger the acid, the weaker its conjugate base. The stronger the acid is means the equilibrium lies farther and farther to the right, means the conjugate base cares less and less about protons. If a base doesn't care about protons, it is a weak base. How do I know if an acid is a strong acid? I cannot go to the equilibrium in the water and look at which one transfers 100% of the protons. Well, luckily, people did that for us. Out of all the acids we will encounter, only 7 of them are strong acids. All other acids are weak. Therefore, you should memorize these 7 strong acids. Again, all other acids we will encounter in this class are weak acids. Now let's talk about a weak acid. Again, we're going to use this acid ionization equilibrium to talk about it. Remember, the definition of a strong acid is an acid that donates 100% of its protons to water. In that case, this equilibrium lies far to the right. In the solution of a strong acid, basically there's no acid molecules. All molecules are ionized into ions. Weak acid transfers only a small percentage of its protons to water in the aqueous solution, usually less than 5%. Oh, 95% of the weak acid molecules will stay as molecules. Only about 5% are transferred, ionized, becomes the ions, becomes conjugate base. Well, if that's the case, only 5% or less protons are donated. Therefore, this equilibrium will lie far to the left. So the equilibrium lies far to the left. Majority of the molecules stay as molecules. Again, the weaker the acid, the stronger its conjugate base. Okay, similar to the one we just discussed on the last slide. The stronger the acid, the weaker its conjugate base. The weaker the acid, the stronger its conjugate base. In the water solution of a weak acid, most of the acid molecules stay as molecules, only a small percentage ionized into ions. Makes sense. A picture showing us the species present in water when a strong acid or a weak acid is dissolved in water. So on the left, it is a strong acid. When you dissolve a strong acid in water, goes into water, the molecules basically disappeared. They are all ionized. They all become hydronium ion and the conjugate base of the strong acid. There is no molecules inside the solution. Well, there are water molecules, but we're talking about the acid molecules. For a weak acid transfers only a small portion of its protons. So if you take the weak acid molecules, dissolve it in the water, majority of the molecules will stay as the molecule itself. Only a small portion becomes its conjugate base. I hope that makes sense to you. Identify the chemical species, except water, in the solution when each of the following acids is dissolved in water. Okay, they will give us some acid and access what are the species exist in the solution. How do we know the answer? We're going to looking back to these 2 charts here. We're going to figure out if the acid is a strong acid or weak acid. If it is a strong acid, we use this chart to make our decision. If it is a weak acid, we use this chart to make our decision. Let's move on. HCl. HCl is a strong acid. How do you know that? It is one of the 7 on the last slide. I memorized that. All right, if it is HCl, once it is dissolved in water, there's no molecules anymore. All of them will become hydronium ions, and the conjugate base of the strong acid, in this case, it is going to be Cl negative. These are the species who exist in the water solution of HCl. Of course, there is a lot of water molecules. However, the question tells us, do not count that. Do not ignore the water. What other species you have? B, HAC. Well, HAC is a shortened form for acetic acid. The true molecule for acetic acid is CH3COOH. It is a monoprotic acid. The hydrogen on oxygen is acidic. The other three hydrogens are on carbon. They are not acidic. So it is a monoprotic acid. Acetic acid is actually the acid in vinegar. All right, so HAC, acetic acid, it is a weak acid. How do I know it is a weak acid? Again, it is not one of the 7 acids on the last slide. So here we go. Majority of the acid will stay as the molecule. So we're going to have the molecules HAC, or you can write that one, that's okay. But HAC is easier. We have this molecule. We also have a small portion of the ions, only a small portion of the molecules ionized into ions, transferred protons. So we're going to have this hydronium ion. We're going to have the conjugate base of the weak acid. You can simply use AC negative to represent acetate. Acetate is actually CH3COO negative. But just use that. Out of the 3, they can also ask you which one is in the greatest amount. You know the molecules. For the weak acid, the molecules is in the greatest amount compared with hydronium ion, compared with acetate ion. Again, there are water molecules. Water molecules will be the one in the greatest amount. However, it says that except water, ignore it. Now let's talk about bases. Strong bases, only the hydroxides of group 1A and 2A metals are strong bases. Only they, when dissolved in water, will give up all of their hydroxides. Well, these are the hydroxides for group 1A metal. For hydroxide from group 2A metals, only 3 of them are listed here. 2 are missing. That's because those hydroxides of those 2 compounds are not water soluble. They cannot dissolve in water. Out of all of these strong bases, the most common one is the one that we or everyday people will encounter are these 2. Sodium hydroxide, potassium hydroxide. Those are the 2 most common strong bases. Almost all other common bases are weak. Now let's talk about a weak base. This is the generic ionization process of a weak base in water. B represents a weak base. It is getting a proton. It's the base. It is a proton acceptor. So water is going to donate a proton to it. A proton is going to go from water to it. The base is going to get a proton, becomes BH plus. Water, after donating a proton, becomes hydroxide ion. Wait a minute. The equilibrium sign, this is probably the first time we see this. Okay. Usually the equilibrium sign symbol is like that. Well, sometimes you're going to see this. Sometimes you're going to see that. An equilibrium like that tells you it favors to the left. A symbol like that tells you it favors to the right. So right now we're talking about a weak base. the equilibrium favors to the left. That's why the symbol is written like that. The most common weak base, which is probably the only weak base you're going to see, you're going to encounter in this class, is ammonia. And here is the acid ionization, here is the ionization equilibrium of ammonia. Ammonia is getting a proton from water. NH3 becomes NH4 with a positive sign because a proton carries a positive charge. Water, after donating a proton, becomes hydroxide. I hope you can relate these two together. Okay, the first one is the generic equilibrium for a weak base. The second one is the equilibrium for ammonia, the most common weak base. What is the most abundant species, except water, in the aqueous solution of ammonia? Okay, here is the equilibrium. What happens when you dissolve ammonia in water? It is a weak base, so it favors to the left. The symbol tells you it favors the left. So which one is the most abundant species except water? Of course, ammonia molecules. All right, let's move on. This last slide is practice. 3 practices. In each case, it is using generic acid, generic base, be it strong or weak. Try to complete them by yourself. Okay, refer back to the videos, to the previous slides. Okay, once you're done, pause the video, do them. Once you're done, check the answer key. I'm sure you can do this. All right, see you next time.